Let us now calculate the RMS value of a sinusoidal AC. Again, we can consider sinusoidal AC as I is equals to I naught sin omega t, where I naught is the peak value. And if we plot the function, this function as a sine curve which looks like this. For half cycle, that is t by 2, and then next half cycle is t, then 3t by 2, and so on. The current is oscillating between plus I naught and minus I naught. If we calculate the mean square value, you can see the mean square value, if we square it, the function will be varying with the same period, but half cycle, the value will rise to a peak value I naught square, and then for the next half cycle, again it will rise to the same value. Or you can say, even if the direction of current is opposite, if we square it, the sine of I square will remain same. So we can write, after every half cycle, the direction of mean square value is not changing. So its period changes to half also, and it is oscillating between 0 to I naught square. So here it won't make any difference if we calculate the root mean square value for half cycle of the AC or for the full cycle of AC. It will remain same, because in the next half cycle the function is repeating itself. So here we can write RMS value of AC. This AC we are calculating whether it is half or full cycle. It will not make any difference, it will remain same. This I RMS can be given as this is root of I mean square value. And this mean square we can separately calculate as the mean of squares. It is 1 upon t by 2 integration from 0 to t by 2. I square dt, which is I naught square sine square omega t dt. So here we are calculating the average of squares, then by using this we can find out the RMS value. Here if it is further simplified, it is 2 I naught square by t integration 0 to t by 2 sine square omega t, we can write as 1 minus cos 2 omega t by 2 dt. Now if we integrate the function, this mean square value, here we are getting is 2 I naught square by t, and this will be t by 2 minus sine of 2 omega t by 4 omega. And we substitute from 0 to t by 2, again we can write as pi by omega. Now we substitute the values over here, see what we are getting, 2 I naught square. And here this time period can also be written as 2 pi by omega. And you can see a second term is becoming 0 because it is sine 2 pi or sine 0. Both terms will be 0. So here we have, if we substitute the value of t as pi by omega, this will be pi by 2 omega. And here you can see this omega gets cancelled out. And finally see what we are getting here. Pi also gets cancelled out. This is I naught square by 2 we are getting, when 2 also gets cancelled out. So this is the mean square value. Then from this relation here we can see the value of I RMS is root of I naught square by 2. So we can see for a sinusoidal AC, its RMS current can be given as I naught by root 2. Similarly, if we are given with the AC EMF, then in that case, RMS value of EMF can be written as E naught by root 2, where E naught is the peak EMF of AC generating device or AC generating source. So this can be written as root mean square value of the AC EMF. So this is also going to be used in many cases. So you must be careful that for a given sinusoidal AC, and you should also remember, even if there is some phase associated, like if it is I naught sine of omega t plus pi, then also we can say it won't affect anything on the function. So RMS value will remain same. And even for half cycle or for full cycle, the value of root mean square sinusoidal AC will be same. The same is also termed as effective value of an alternating current.